Hey, all. Today we are going to do one last discussion about hypothesis tests, and this time we're going to talk about hypothesis tests for linear regression. So a long time ago this year, we discussed the relationship between two quantitative variables. We made scatter plots, we created linear models, we made predictions using those linear models, and today we're going to discuss hypothesis tests for those. We probably won't go as in depth on this one as we did for the previous ones, but just to give you an idea of what a hypothesis test for regression will look like. So as always, we need hypotheses. We're going to be making judgments based on the slope. The slope is what relates the two variables, that shows some sort of change in one variable as it relates to the other. And so we will go into a t-test for a slope. By the way, it's a t-test. We will go into a t-test for a slope with the assumption that the slope is 0, meaning there's no relationship. And we will look for evidence that there is a relationship, and that would show us that the slope would not be 0. So we have to make some assumptions and conditions. We need our data to look straight, much like we did in the past when we were talking about correlation. We need our data to be randomly sampled or collected through random means. We need our residuals to be random. So remember when we plotted, made a scatter plot, we put a linear model on it, and the place or the distance between each individual data point and that linear model was considered an error. We called it a residual. The data points on a scatter plot are the things we actually observed. The line that we would fit to it would be a prediction model. And so the distance between what we observe and what we might predict is called a residual, an error. And what we are trying to do when we create that linear model is get some consistency in the errors. And actually, if we skip ahead here, this equal variance condition, we want the data to look around the line like there's some sort of consistency in how far the data points are from the line. So we wouldn't want to look at one part of the graph or the plot and see big residuals, and then if we look on the other part of the plot, we see small residuals. We want some consistency throughout the plot. We need the independence, we need the residuals to look random, and we need to fit some sort of normal condition. We're not going to be doing a lot of this by hand. But what we would check for normality would be a histogram of the residuals. Yeah, so those are our assumptions and conditions. So let's look at an example here. Take a second to read this. So we're looking at a plot. And the relationship we're looking for is how many years we've gone since the year 1970 and our ability to successfully predict hurricanes. And we get a computer model output over here. And we've read these before, but it's good to go over them again. We are going to be creating a linear model. So something in the form of y equals mx plus b. And of course, when we do the model in statistics, we put the intercept first. What we did in algebra as b, that came last, we would put our intercept first. And so when we see intercept here, this would be the y-intercept of our linear model. Years since 1970 is the variable, the explanatory variable, our x as we're used to it. And so this would be the slope. That would be the coefficient of our variable, negative 2.01. We have some standard errors here, and then we have some t ratios, some t values, and some p values. And these are associated with our hypothesis tests. So we actually have the p value. The probability, in this case, would be the probability there's no relationship or the probability that we get the results that we have if there really is no relationship between hurricane tracking and how far we are from 1970. And so our regression model would look something like this. I think we'll say hurricane prediction. I'm just going to do it like this with a hat, remember, because it's not an exact answer. Our intercept minus our slope times, I'm just going to say years. This is years since 1970. So this would be our linear model. So that means that let me see. Are we dealing with error? Sorry, I've made an error. I'm going to make this error. We're talking about the amount of error we have in how far off we are on the hurricane. And so what the slope means is that for every year we get past 1970, our error drops, goes down by 2.01. What the intercept means is in 1970, we were 132.3 nautical miles off of our hurricane prediction. So pretty far off on our hurricane prediction location here. For our slope tells us for every year past 1970 that we add, our error will be less to about 2 nautical miles away from where the hurricane location will actually be. So as we get further along in years past 1970, our error goes down. It looks like we're getting more accurate predictions of the hurricane location. We want to state a hypothesis about the slope. So let me write that and then we'll be back with you. So here are our hypotheses. We're going to assume at the beginning our null hypothesis is there's no change in the error in our predictions over time. And so when we look at our linear model, the way we write it here is mu equals beta 0 plus beta 1 times x. So beta 0 represents our intercept, beta 1 represents our slope. So when we're talking about slope, we're going to say beta 1. So in words, there's no change in the error over time. In numbers, numerically, beta 1 equals 0. The slope is 0. So our alternative would be there's a change in the error over time and our slope is not equal to 0. So we have some sort of slope, positive or negative, that shows some relationship between our years since 1970 and the error we have in predicting the hurricane location. So they're telling us we're assuming the assumptions for inference are satisfied. Our data is straight enough. It doesn't look super, it looks like we, maybe we got some points off the path there, but they're saying they're satisfied. We have a random sample or a representative sample. These predictions are independent. The spread in our residuals is fairly consistent. It does look a little bit larger over here, but they're saying it's okay. And so we can make a conclusion by looking at this output. So we are talking about the slope. So this row on the bottom, and we want to look at this information. The t ratio, that's like we did when we did a hypothesis test for means, an approximately normal distribution where almost 100% of our data is between 1 and 3 standard deviations from the mean. So if we get a t-value of -9, that's really far away from the mean. That means the probability is incredibly small, less than 0.0001, almost 0. We can actually say approximately 0. So let me write up a conclusion and then I'll get back with you. So we're going to reject or fail to reject just like we have been. So when the p-value is small, we reject the null. Our p-value is pretty small, insignificant, almost 0. So I'm going to say with a p-value of approximately 0, we'll use our alpha of 0.05. We do have evidence to show that there is a change in the error over time. So, and if you look at the scatter plot, if you look at the trend here, it does look pretty clearly that as we evolve past 1970, these predictions are getting much, much better. The error in nautical miles is going down pretty consistently in a linear pattern as the years go by. So this is it visually, this is it using probability. And the last thing this problem asks to do, which is something we talked about before, but I think it's important to go over again, is what does R squared mean? So we get an R squared value up here. You got to kind of look for it. R squared is a percentage. It's quite literally the correlation coefficient R squared. So we could find the correlation coefficient if we wanted to by square rooting the R squared value. We're not going to, but we could. And it would probably, or it would definitely be negative. Our correlation coefficient would be negative since we have a negative slope. But our R squared value is always going to be positive. It's always going to be a percentage. And what it is the amount that we can attribute our change in error to the years we've gone past 1970. So 68.7, percent of the variation in our error when predicting hurricanes can be attributed to how far we are from 1970. And of course, there's more that goes into that. The reason why R squared isn't really high here is because just because time has passed doesn't mean that we're going to get better at reducing the errors. Certainly some other things have affected that, maybe technology, maybe experience, maybe data collection. So there's still 30.03% or 30.3% of error to be accounted for. But R squared tells us when we're talking about years since 1970 and error in prediction, that 68.7% of that variability in our error is accounted for by the years since 1970. Surely we have that written up somewhere. I believe it was in Unit 2 when we talked about regression. So if you want to refer back to that, you can. Right now, we're mostly focused on writing up these hypotheses and making a decision based on an output. For our purposes, we won't be calculating this stuff. We'll be looking at computer outputs. So when I give you examples, you'll be looking at the computer outputs, much like this, and having to locate the p-value, having to locate intercepts, the coefficient, writing up these hypotheses in context, in words and in numbers. So remember, beta represents the slope. And then drawing your conclusion like we have been doing based on our p-value, based on a significance alpha, and using our context to make our interpretation. So I won't be here when you're watching this probably, unless you're watching it beforehand, and I still won't be there. So do write down any questions you might have for when I return. Do stick around and answer the questions associated with this problem. You can find this problem on Canvas in the text chapter 26 if it's difficult to read on your screen. This is problem number 12. Make sure you answer the questions, write down any questions you might have, and then make sure you do the practice problems, please, because practice is what makes you proficient. Good luck.